Well, I'm very pleased to be here and honored and honored and intimidated to be trying to summarize this meeting. Here's an outline of what I'm going to do. I'm going to offer thanks, as many other speakers have done, but in a slightly different way. I'll make some general observations. I will survey the topics covered in this meeting, and I will make apologies already for not summarizing the gong show. Trying to summarize the rest of the meeting was already enough of a challenge. And also apologies both for my limited understanding of what people said that I might accidentally misrepresent, and I've had to make some choices of which topics to emphasize, and they might not be the topics that other people would have chosen. So one of the things about giving a summary talk is that I get to steal from absolutely everybody else, and I decided to steal from Greg Moore's quotes of Yogi Berra. So I could thank everyone who made this day necessary, or made it necessary to summarize the other talks. I would like to thank the organizers, not really for inviting me to speak, because it's kind of a thankless task, but for doing such a good job inviting all the other speakers who gave particularly clear, interesting, and informative talks, and made the task of listening to them, paying attention, and really trying to understand what they were saying interesting and very pleasurable. I thank the other speakers for also making this task so interesting. And I thank everyone who made the conference run so smoothly, because I think it's really been a great pleasure, and maybe Paula will have something to say afterwards as well, but I'd like to just offer a hand to everybody that ran the conference. So a few observations. Several people encouraged me to find out whether or not the average age of the speakers here was going up. Certainly for some of the speakers, their age has been going up, but it's not clear that the average age has been going up. And this seemed like a rather complicated task, particularly while I was supposed to be listening to all the other talks, so I did something a little bit easier. I just looked at all of the speakers, and I figured out when the youngest ones got their PhDs. And I defined somebody to be young if they received their PhD in the last decade, roughly. So roughly a third to a half, 2/6 of the review talks and 11 out of the 28 regular talks were by young speakers by that definition. And when I looked through the names and the talks they gave, I think that those were some of the clearest and most interesting talks. So I think that's a sign of health of the field that we have such good young people giving such interesting talks, and maybe a sign, given how clear and interesting they were, that there should be even more talks by people in that age group in the future. I really think that they did a wonderful job. So another observation, in discussions at the breaks, many people have said, well, where are the strings? This is supposed to be a string theory conference. It seems that there aren't many strings in the talks. And that's true from one point of view, but of course in the last 16, 15, however many years, we've learned many new things about string theory. We've learned that it includes brains and many other things, and we've learned that string theory is a large end limit of gauge theory. So while many of the talks could have perhaps derived some of their results without any reference to string theory, they often used ideas, techniques, boundary conditions, insights from string theory, and they had implications for string theory and for brain theory. After all, there was a lot of focus on n=4, maximally supersymmetric Yang-Mills theory, on the 0-2 theory, and these are the theories that live on the D3 brains and the M5 brains of string theory and M theory. We also heard a lot about ABGM theory, which describes the dynamics of multiple M2 brains. So thinking that we're only studying supersymmetric gauge theory is not really accurate. We know in string theory compactifications that there are all sorts of interesting BPS states, non-perturbative effects that come from wrapping brains on cycles of the internal space. And the sort of constructions that we've heard a lot about at this meeting are certainly relevant to that broader picture of string theory and M theory. We've also heard a lot about ADS-CFT, and most of that analysis has also been done in the gravity approximation. And so again, you might say, where's string theory? Haven't we just taken the alpha prime goes to zero limit? And that's often the case, but it's not because we shouldn't be doing string theory. It's because string theory in these situations is often intractable. Or at least very difficult. And so the fact that we're doing gravitational calculations is really because we're doing a low energy approximation to string theory. And eventually, we would really like to solve string theory in these backgrounds. So I think if you think in this broader framework that really most of the talks have been about string theory sufficiently broadly interpreted. Another thing that sort of occurred to me, relevant to some of the talks, is that we've seen in some cases a triumph of just hard work and conservative approaches rather than more speculative approaches. So I think a nice understanding of this is a nice example of this is the understanding of the n to the third 3/2 behavior of the number of degrees of freedoms on n M2 branes. And I think many people thought or hoped, including me, that understanding that might require some radical reformulation of quantum field theory or some generalization of quantum field theory. And of course, there's the beautiful work of Gustafsson and Bagger and Lambert involving 3 algebras. And that, initially suggested that maybe you really did need some kind of exotic new structure. But understanding this, it turns out, really required a reformulation of these theories in more standard language, progress in localization, which was an impressive and very technical accomplishment, and the application of one to the other. So we've now understood that, but not by going to some radically new framework, but just by doing very hard work in a more conservative approach. The love affair between math and physics has obviously gone from a fling sort of thing that in the 1960s into a serious committed relationship. And at least according to a movie, which I'm afraid I haven't actually seen, and I don't know which of these attractive people is math and which is physics, but evidently from the title, it's not possible to have this kind of relationship without string theory. I mean, it's really remarkable that the recent developments in mathematics, and by recent, I don't mean 20 or 30 years ago, but many of these developments are 5, 10 years old, are being linked so closely to developments in string theory, the study of amplitudes, black holes, supersymmetric gauge theories, the amazing results that we heard about amplitudes. These include things like quantum dialogues, Mach theta function, cluster algebras, mixed Tate motives, a whole long list of subjects that I think even mathematicians didn't know much about in not long ago. And so this relationship has become very, very beautiful and intricate. This part of string theory, or what's usually called string theory, it seems to me, follows its own internal logic. It doesn't really operate by the standards of physics. That is, it's not concerned with comparison to experiment, although it's delighted if experimental results end up being relevant, or it can be applied to experimental results. And it really doesn't focus on rigorous proofs, but nonetheless, it's a rich source of ideas and non-trivial results. And it motivates new results, both in physics and mathematics. Of course, this has been going on for a while, but it seems to me that the pace of this development has accelerated, and really this was one of the main topics at this meeting. The physical side of string theory has moved, it seems, more in the direction of ADS-CFT, of applications of ADS-CFT to the strong interactions, to condensed matter, to fluid dynamics. And we heard a number of talks in the last couple of days about attempts to apply it to cosmology and inflation. So does this mean that string theory unification is dead? We heard only a couple of talks that were really related to model building and string theory as a unified theory. Well, to quote a famous Monty Python sketch, no, he's not dead, he's resting. But unlike the parrot in the sketch, it seems to me this is probably the case with string unification. The landscape problem has made it very difficult to make precise predictions, and that may well be the answer, and anthropic arguments may be correct. But personally, and I'm unlike other speakers, I'm just going to speak my mind in some of these issues. It seems to me that it's unlikely that we're going to be able to do science in a good way, and there may just be some things that we can't understand. So I think the revival of string unification, which I think is quite possible in the future, is going to require either data from the LHC, dramatic breakthroughs in our understanding of string vacua, and of course the best thing would be if it involved both. So I'm going to now move on and give a summary of some of the material discussed at the meeting. And the daunting task here is to figure out how to organize 5 long days of talks or 4.5 long days of talks, an opening talk, 6 reviews, which were very clear, 28 regular talks, and some number of gong show talks. So I came up with various methods to organize the talks, metrics that I thought might be interesting, useful, and amusing, and I came up with the following list. So we can classify them by the length of the talk, and the natural unit there would be the decigross. We could classify them by the number of slides. The natural unit there would be the centimore. The degree of difficulty, which is so difficult that I don't actually know what the unit is, but I know that it's spelled with the Cyrillic alphabet. Then there's the number, sort of a measure of excitement, the number of exclamation points, which is naturally measured in nanowaffe. And finally, there's the clarity of the talk, and I think the only appropriate unit there is the pico-elvang. So, survey of topics, and as I said, I'm not going to obey the rules of Swedish neutrality. So, scattering amplitudes. This was some of the first talks that we hear, and this is a continuation of the rapid progress over the last few years, and to the outsider, and I'm definitely an outsider, it's really just an amazing tour de force of technical and deep, surprising structures and results. We heard about connections between amplitudes and geometry, which have been developed over the last couple of years, completely new ways of thinking about and rewriting Feynman amplitudes. We heard about the remarkable application of Goncharov, which leads to simplifications beyond the already remarkable simplifications. And it seems clear that there's going to be eventually a reformulation of perturbation theory in field theory, certainly in special quantum field theories, but a lot of the structures seem more general, and we've heard about more general applications of it. And the final formulation is still unknown, but it doesn't seem unlikely that 4 or 5 string meetings from now, we'll be hearing about a very elegant, different way of thinking about quantum field theory that will end up in textbooks. And as in the past, I think this is at least the third, maybe the fourth time when results from string theory or supersymmetric field theory have led to new results in methods of calculating perturbative Feynman amplitudes. These techniques feed back into practical calculations that are required for the understanding of QCD background effects. So there's a kind of technology spin-off. We also heard about new developments in n=8 supergravity using these techniques, using the remarkable relationship between n=8 and the square of n=4 amplitudes, and full analysis and application of the E7 symmetry. So the real question there is n=8 a finite theory of gravity? And in answering that question, I think we should apply standards that are at least as strict as those of the Catholic Church. So if we think of n=8 supergravity as kind of a theory that we want to promote, we want to canonize it, see if it's worthy of sainthood, and the canonization procedure requires either martyrdom or a miracle. And I guess one could be of two minds about that. Certainly miracles have been claimed for n=8, but you might also argue that it was martyred by string theory. In any event, once you have the martyrdom or a miracle, you then qualify for beatification, and a second miracle is required for official declaration of sainthood. So it was previously thought, either through martyrdom or through the miracle of the lower loops, that it qualified for that first step of beatification, but instead it turned out that miracle was just a consequence of symmetry. So now, with an improved understanding of the counterterms, it seems that a new miracle is required at 7 loops. At 7 loops, and the analysis of counterterms, we have terms which are completely non-BPS. To me, this seems unlikely, but it remains an open problem requiring either understanding of even more and deeper symmetries or some, not really one, but I think an infinite sequence of miracles. If that happens, then n=8 should be canonized and turned into a saint, but it seems to me that that is unlikely to happen based on what we've heard here. The study of amplitudes in n=4 super Yang-Mills, of course, is a part of a much grander plan, which is the attempt to solve the planar limit of n=4 super Yang-Mills for all values of the 't Hooft coupling. It's, to me, an incredibly ambitious and amazing idea that one should be able to do that, or might be able to do it. But it seems from recent developments that when you combine perturbation theory, ADS-CFT, integrability, conformal symmetry, dual-conformal symmetry, Yangians, and a bunch of other things that I don't really understand, and it seems to me occasionally a few lucky guesses that this might actually be possible. I mean, what are other models that just get solved? I guess the Ising model, and solving the Ising model was certainly an amazing step which led to all sorts of insights into phase transition and condensed matter physics. This is a much grander scheme than that, but it doesn't seem impossible. And I hope that maybe I'll hear about that in some future strings meeting. So there's another area which received a lot of attention here, and that's what Greg Moore in his talk called physical mathematics. We heard about new connections between old subjects, the revival of n equals 2, which I think was featured at the last strings meeting and continues here. The 0-2 theory on multiple M5 branes continues to be a source of new ideas and inspiration and results. The philosophy seems to be if you see a manifold, wrap a brane on it, and if you see a path integral, localize it. It's not easy to do, but that's what you're supposed to do. We also heard about some remarkable results that I find very intriguing involving moonshine, connections between sporadic groups, and string theory, which we have known about for quite a while, but the previous results involved compactifications down to 2 dimensions and can be embedded purely in the bosonic string. The new results are definitely linked to supersymmetry. They involve symmetries of K3 surfaces that preserve the symplectic structure and so preserve space-time supersymmetry. And I find it very intriguing that very special string compactifications down to 6 and perhaps 4 dimensions are now being linked to some of these very deep and interesting mathematical structures involving sporadic groups. I don't understand what's going on, but it seems like we'll see some interesting new directions there. So the impression, to me, when I hear all this stuff is just, it's kind of amazing. Mach modular forms, Kolvanov, homology, framed BPS states, motives, all these things. And I've enjoyed hearing about all this progress, which I was kind of aware of, but didn't see the details of. And all this stuff that's going on brought something to mind, the way Mike Duff said that sometimes you get a song going through your mind when exposed to certain things. And the song that was going through my mind is a song by Bob Dylan. I'm not going to sing, I can't do that. You walk into the room with your pencil in your hand. I was more or less doing that. You try so hard, but you don't understand just what you'll say when you get home, because something is happening here, but you don't know what it is. Do you, Mr. Jones? And I don't think he was talking about Vaughn Jones in this song. It's actually about being harassed by reporters, but it seemed very, very appropriate to the way that I felt. There's clearly something going on. I don't understand what it is, but it looks very deep and beautiful. So moving back to the physical side, we heard a number of talks that I've kind of linked together in somewhat unrelated way, but they often involved cosmology or de Sitter space. So the fact that we have this inflation model, which seems very successful in some ways and very promising, and the observed accelerated expansion of the universe makes it clear that we need to face up to understanding cosmological solutions and de Sitter space, in particular, in string theory. And we heard a number of developments in this direction. We heard about, well, this is somewhat indirectly related, but we heard about the ghosts of conformal gravity being somewhat less scary, at least at the classical level, because of a way of embedding solutions of conformal gravity into those of regular gravity. We heard about the construction of metastable solutions within string theory, and there's the issue of back reaction, and I must say the answer was subtle. It was complicated, and I don't really know how to summarize it other than it's not an easy question to answer. There was a nice talk about the search for kind of minimal de Sitter solutions in string theory, ones that are under better analytic control, where we can compute reliably and have a really firm grasp of what's going on. But again, it's hard, and all the models that were constructed had tachyons. Now, a skeptic of the landscape multiverse, and I don't know if I'm skeptical, but I wouldn't say I love it, might take some hope from these results. That is, that maybe there aren't as many points in the landscape as you might have thought, particularly once we break supersymmetry, but it's obviously kind of early to really know what's going on. But I think these kind of developments are very encouraging and a very worthwhile direction to pursue, or keep pursuing. To some degree, I'm just, quoting the summaries of various talks, but I don't know what else to do when I'm trying to do this. So, related to this is the fact that inflation probes Planck scale physics. It's a natural place to apply the ideas of string theory. And there are constructions now of how to do that, KKLT type constructions, but they're very, very complicated, and not all of them are really sensitive to the UV completion. At least we heard about that in a kind of statistical sense, where you survey a landscape of possible models of a certain class. Other models are, and we heard about the development of tools that would be used to confront exceptions to some of the observations that have been made now with string or supergravity-inspired inflation models. So let's hope that we have some of that data in the near future. We also heard about studying tunneling and the role of warping, but that was the talk right before. If I have to summarize that, then your attention span is even shorter than mine. Now, we heard about the standard model and beyond the standard model physics. We heard a very nice review of what's going on at the LHC. Things are encouraging in terms of the luminosity, exceeding what we might have expected. And we are in the amazing situation after a long, long wait of expecting the Higgs, at least in this kind of light window, to show up by the end of this year or sometime next year at the very, very latest. That's a remarkable thing to me. And, we'll have to see what happens. The prospects for low energy supersymmetry seem a little dimmer in a statistical sense, but of course, multiverses to the contrary. We live in one universe. The LHC is at least built in one universe, and the parameters have what value they have if low energy supersymmetry is correct. And we don't know the measure on the space of, parameters that enter into the MSSM, so the jury is still out, and we'll just have to wait and see. Something expected would be delightful, of course, and I think it's a very exciting time, but also nerve-wracking to see what the LHC will see. It's conceivable that they find nothing, no supersymmetry and no Higgs. That would be exciting, because not finding the Higgs means that we don't understand something about the standard model and about particle physics, but that excitement is going to be very, very hard to sell to some people. Why is finding nothing very exciting? It goes contrary to what we expect. Finding just the Higgs, of course, would be the sort of basic thing, but then it leaves us without knowing how to go beyond the standard model. But I think we still have many reasons to expect that there is physics beyond the standard model, whether it's supersymmetry or something else. So, the next couple of years we'll be biting our nails waiting to see what happens. We also heard about problems of the standard model. I think problems that we all have heard about in the past, but it's good to refocus our attention on them. These are forms of, might call them old new physics. That is, they're somewhat old approaches to what might be the new physics, grand unification, supersymmetry, axions. But to me, that kind of emphasized the fact that we've made great progress in understanding problems that we used to think were very hard, which is understanding the dynamics of non-trivial theories, understanding gauge theories at strong coupling, really remarkable things, which I think in the past we would have thought were much harder than understanding something like the CKM matrix, or neutrino masses, or the ratios of couplings. But apparently that is not how the world actually works. Somehow understanding those couplings is a much, much more difficult problem, perhaps an impossible problem. That doesn't mean we can't do physics. Dynamics is physics too. It just means that some parameters may be very hard to understand. So we heard about aspects of supersymmetric theories. We heard a lot about this, of course, in the connection between math and physics, the physical mathematics, which often uses supersymmetric gauge theory as a tool. But we also heard talks about in particular supersymmetric theories on spheres as a way not only of doing mathematics, but it's probing the dynamics of the theory, looking for new observables, and providing various non-trivial tests of a number of dualities that have been proposed. And we heard in a very elegant way how a number of these different treatments can be unified and using the formalism of supergravity and auxiliary fields. And we also heard about the resurgence of localization, not only in math, but as a way of understanding supersymmetry in more physical situations, a tool which it seems is going to be applied in a lot of interesting new ways. We also heard about black holes, and I think this is really a great triumph of string theory. The talk that Ashok gave was very technical, but when all those big, complicated numbers match up, become positive, do all these nice things, it leaves you with a feeling that whatever else string theory is or is not, it's definitely a theory of quantum gravity that gets at some of the key issues of quantum gravity, namely, how is it that black holes, how do we understand the black hole entropy from a microscopic point of view? And the techniques that have been developed to compare the counting using microscopic techniques and space-time techniques lead to new insight into general relativity, new insights into string theory, remarkable mathematical structures, again, particularly when you have n equals 4 or n equals 8 supersymmetry, and are counting states that preserve some of the supersymmetry. So we heard, more precise tests away from the large charge limit, that you can look at the sign of the index, subtle logarithmic corrections to the entropy. And to me, it's really quite an impressive accomplishment. There are some interesting future directions involving generalizing the techniques of localization to non-rigid theories, to supergravity theories, to superstring theories, trying to do these kind of counting for n equals 2 theories. I mean, our eventual goal, maybe not the eventual goal, but one goal would be to understand the entropy for non-supersymmetric black holes. That doesn't seem impossible given all the recent progress. So string theory and quantum gravity seem quite happy together. I list these topics in a sort of humorous way as recognizable to a pre-1998 string theorist. Really what I mean by that, or what I was thinking about there, is that someone who fell asleep for 15 years, a kind of Rip Van Winkle of string theory, coming to a meeting like this would really not know what was going on in most of the talks. Our view of what string theory is and what questions are interesting have changed so dramatically in that time. But there are a number of very interesting and important problems left over from before the revolutions of duality and branes and ADS-CFT, and many of them are still very worthy of attention. So we heard about more general string compactifications. We heard about developments of the doubled formalism with manifest T duality, something that may have applications in understanding other dualities. And one of the problems left over from that time that really is still, sort of the focus of trying to connect string theory to low energy physics, to connect string theory to cosmology, is the problem of moduli stabilization. Some progress is being made, but it would be great to have simpler models. Earlier, I talked about an example where really a tour de force of technical work ended up with giving us an answer. It's not clear whether that's the case here, whether we need new ideas, or the situation is just the way it is, and we're stuck with that. Now, one of the topics that I think received the most attention, probably the most talks here, was the general area of gauge gravity duality. Its applications, its generalizations, and the range of applications and ideas that this is being applied to is really quite remarkable and has increased dramatically in the last couple of years, particularly in condensed matter theory. So we heard about the study of quantum critical points, of course, the computation of transport coefficients, conductivity, the viscosity to entropy ratio, of course, is the classic one that brought a lot of fame to this area. We also heard about attempts to move beyond conformal field theory by perturbing conformal field theory, which of course we are familiar with from the early days of string theory and conformal field theory, but are now being applied in this new context. It's kind of amazing to me to hear a condensed matter physicist stand up and talk about how they're going to use ABGM theory to study non-Fermi liquids or whatever. I'm not sure I got the system right, but nonetheless, it's remarkable to me that you can say this with a straight face and that people can sit there and listen to it and say, yes, that makes sense. It's a remarkable development. So it's also, leads to prospects for confrontation with experiment, in a sense, testing black hole physics in the lab, because the dual descriptions of these systems definitely involves black hole physics. Now, in listening to that talk, I was, reminded of some of the problems that face a subject that we really didn't hear much about at this meeting, and that's the area that's the origin of string theory and one of the early applications of gauge gravity duality, namely QCD. And a number of the problems that will undoubtedly confront applications to condensed matter physics have also been confronted there, and many of them have really not been dealt with satisfactorily there either. We need a better understanding of string theory and curved backgrounds. Worrying about the back reaction of matter fields, well, often what you do is you look at some brane configuration that represents pure QCD without matter, and then you add in some other branes, but the back reaction is hard to deal with. The inclusion of higher spin fields. Here's one of the pictures that eventually led to string theory, the very straight line in a plot of angular momentum versus mass squared for a tower of mesons, the rho, A, omega 3, A4, et cetera. And this kind of plot, and if I'd included the daughter trajectories, it would be even more obvious that there are problems in this that are not going to be dealt with using the formalism we now know. So in particular, I think we can hope for, even expect, qualitative understanding of various phenomenon, perhaps including some phenomenon that didn't previously have even qualitative explanations in condensed matter physics, in a way that's similar to the way that we can understand confinement and chiral symmetry breaking using ADS-CFT in very, very general ways as general properties of metrics and brane configurations. But as in QCD, there's generically no separation of scales between gravity and string theory. There's no gap in the spectrum of anomalous dimensions. If I go back to this picture, there's no gap between the daughter trajectories, which are kind of Kaluza-Klein-like excitations, and the higher spin excitations. They all have the same energy scale. So, really in these condensed matter applications, presumably one is in a similar situation and should be solving string theory rather than just gravitational theories. But sometimes we're lucky. Sometimes we better find good agreement without a very good understanding of what the small expansion parameter is. The epsilon expansion is a often noted example of that. And it may very well be here that we find better numerical agreement than we have any right to expect. Some of the simplest models that are dual descriptions of QCD give properties for the low-lying spectrum and couplings that are accurate to 10 or 15%, even though it's not really clear why. So we can hope for that developments there. As an example of going beyond the gravity approximation, which we clearly need to deal with at some point, we heard about advances in the computation of three-point functions for massive string modes in ADS-C using semi-classical techniques. And we also heard a talk about very elegant application of ADS-CFT to a kind of intriguing new area, the entanglement entropy. This also seems to have fascinating possible applications in condensed matter physics. And I think it's also led to a number of new papers and results in lattice gauge theory because it gives you a new observable to look at. And it's been checked numerically. I mean, it makes predictions. They're tested using experiments. The experiments are done numerically with computers, but they're still experiments. Now, another general sort of topic that many people have worried about, and we heard about from Eric Verlinde, is the question of how general gauge gravity duality is. Of course, there are general arguments for a holographic description of gravity in any situation, and many signs that there should be such a general structure in string theory. The connection between open and closed string theories is one example of that. We have specific examples of these phenomenon in ADS-CFT and matrix theory, but I think a general understanding is a very challenging problem that is going to be a long time in coming, if it comes at all. But we heard, to my mind, an attempt to use these ideas using analogies to matrix theory to get the general outline of some of the properties that such a theory might have. Whether that pans out or not, we will presumably know in the next few years. Now, another direction, which is related to ADS-CFT, but kind of taken on a life of its own recently, is fluid gravity duality. The old membrane paradigm developed before ADS-CFT suggested a connection between gravity and hydrodynamics in that you could describe a region near the horizon of a black hole as a kind of dynamical object which obeyed equations similar to those of fluid dynamics. But there were unphysical properties here, in particular, that in that paradigm you have a negative bulk viscosity. Black holes embedded in ADS spacetimes via ADS-CFT now give a consistent framework which generalizes this idea and is more specific and leads to definite predictions for these transport coefficients that have physical values, and has led to a more direct connection between gravity and hydrodynamics, both relativistic and non-relativistic. And there are interesting developments here. You can consider fluids with anomalous currents. There are new terms which apparently were not there in the standard textbooks, although I guess that's not that hard to understand because it's hard to find liquids that you can study that have anomalous currents and are relativistic. But nonetheless, I think it's quite striking that, coming from string theory, coming from ADS-CFT, people found results that didn't fit into the standard framework and had to generalize it and find equations that probably will end up in textbooks on hydrodynamics. And there are potentially new interesting effects in the presence of parity violation. Now, to me, a couple of very interesting questions are whether you can experimentally realize this in some way. You can imagine things involving axial currents and QCD dense systems, but it would be fascinating if we could really test some of this. And we also heard some very interesting and speculative ideas on trying to constrain higher derivative terms in gravity using some of the techniques that were used to classify the possible forms of these corrections. It wasn't mentioned at this meeting, but I can't resist pointing this out. There's a recent paper by Lehner and Pretorius who studied numerically the Gregory-Laflamme instability of black strings in 5 dimensions. And these are plots, roughly speaking, of the horizon of the black string. And it's unstable. You see that it wants to kind of bulge out here. But then, of course, there's some string left, and then that string wants to develop little bulges, and then there's some string left, and the bulges, other string develops little bulges. And what they find by tracing this numerically through several iterations is that you develop a kind of self-similar structure, and you develop this, and you go down, and you get down to sort of infinitely small scales in finite time as measured by an outside observer. So they find indications of a generic violation of cosmic censorship, which I think is extremely interesting because it means, at least in 5 dimensions, there's the possibility of seeing the small-scale structure of gravity without it being hidden behind a horizon. And it looks remarkably like experimental results from my colleague Sid Nagel and collaborators in the pinch-off of drops of ordinary water and glycerin. When you pinch off a drop of water, it develops a very long neck. But then if you look at that neck in more detail, that neck develops a neck. And if you look at that neck develops a neck. And you get a self-similar structure here with necks and necks and necks until you go down to a singular configuration joining onto this nice round drop at the very bottom. To me, the similarity between these structures is really remarkable. I would love to see someone take these ideas of fluid gravity duality and explain why these two pictures look like each other. It's really quite remarkable to me. All right, so that's really all I have to say. I'm happy to take questions, although taking questions in a summary talk is a little unusual. So maybe there won't be any. If there are any questions, though, I have 2 answers to offer you, again from Yogi Berra. First of all, I wish I had an answer to that question because I'm tired of, I wish I had an answer to that because I'm tired of answering that question. And the other one is if you ask me anything I don't know, I'm not going to answer. So thank you very much.